Okay, tutorial 20, we'll start with question 5. From question 5 onwards, we are the focus here is to formulate the differential equation. Of course, after that, then you solve the differential equation, and the important thing here is to understand the context and then try and formulate a DE. Okay, so I will just share some quick steps. Step 1, we have to identify the variables. Question 5 is a simple example. If you read the question, a colony of microorganisms is growing at a rate proportional to the number of organisms. The first part of the question asks us to write down a DE that models the growth of the organism. So it's a very simple context because there are only these few things. And I think it's not difficult to identify that the variables here, we talk about colony is growing. That means we are talking about population. Let's call this P. And we talk about rate, often we talk about time t. So I think that's all that we have, only P and T. So to really, so this is part of the solution now. All right, we'll just say let P be the number of organisms at any time t. So we define P and T in one line. We say, okay, P is the number of organisms, essentially the population, and T is the time. Then step 2, after you identify the variables, then we will try and formulate a DE. I'm try and formulate. Using what? I think this question is rather, there are not too many sentences to decipher. And if you see here, the colony is growing at a rate. So can I then say that the growing rate is actually dP dt is proportional to the number of organisms at any time. Proportional to what? Proportional to P itself. To P itself. So then we need to form equation. I think this one you know well enough, E equals to Kp. After you have formulated, so now this is the first part we done. Alright. Given that the colony doubles in size in T hours, find the total time taken for the colony to triple in size, giving your answer in terms of T. So in order to do that, we then have to solve the DE. Right? Of course, step 3, we try and solve the DE. How do we solve? I think this is, we have done in question 1 to 4. I don't think it's a big problem. We just divide both sides by P because this is the second type. Correct? This is of the type. This one is of the type dy dx equals to fy. Correct? This is of this type. So you will divide both sides by fy, then you integrate. So we integrate 1 over p, integrate both sides with respect to t. Alright? T, time. Then you integrate 1 over p, this is the same as this, k dt. Then integrate 1 over p, you get ln, do not forget the mod p equals to kt plus c. Then you make p the subject, or rather mod p the subject. At this point, if it is a question with no context, where p means nothing at all, t doesn't mean it's time, then you would have to know that p can be positive, p can be negative. But because in this context, p is the number of organisms, p is actually population, I think it's obvious enough that we can justify by saying since p is greater or equal to 0, then p is easily AEKT, where A is actually e to the power of c. Now, if c is any constant, e to the power of c is just any constant. So I can rewrite it as p equals to kt. Alright, so now A is now another constant. Look, what does the question want? After I have found P in terms of time t, small t, now they want you to find the total time taken for the colony to triple in size. That means initially there's 1,000. What is the time when you actually want to find out what is the time when P is 3,000? But first we need to get rid of the A. We need to find A because A is an unknown here. So make use of the initial condition. When t equals to 0, population is actually 1,000. Alright, population is actually 1,000. Then we substitute this in. That means, therefore, A is actually 1,000 because you substitute this in. Correct? Yes. E to the power 0 is just 1. So A is 1,000. So now we are happy. Yes. Therefore, P is actually 1,000 EKT. Next, the question say that, let's take a look at the question. The colony doubles in size in T hours. Double in size in T hours. Which means this. Which means when T equals to big T, the population is 2,000. So therefore, yes, you substitute back there, you will get 2,000 equals to 1,000 EKT. I divide both sides by 1,000. Okay, EK big T equals to 2. I take ln. K big T equals to ln 2. I will get, therefore, K equals to ln 2 over T. Why do I find K? Because now I can substitute K is, P now is therefore equals to 1,000 E ln 2 T over big T. So everything now is in terms of big T, where big T is a constant. Your job is to find what is the value, what is the total time taken for the colony to triple in size. Let's read the question again. Total time taken for the colony to triple in size. Let me move this up. Alright, P is equals to 1,000 E T ln 2 over big T. So therefore, we want to find what is T equals to what when P, population, equals to 3,000. Substitute in, you get 3,000 equals to 1,000 E T ln 2 over T. If I say 1,000, take ln on both sides, you get ln 3 equals to T ln 2 over T. Therefore, T equals to ln 3 over ln 2 big T. Therefore, you get the answer here. Give a condition under which the model may be inappropriate. This is the tough part, right? This is the tough part. Now, what model are we talking about? The model we're talking about here is this idea that here, this is the most important, this is the model, that the population is increasing at a rate that is proportional to the number of organisms. Actually, intuitively, it makes sense. How many organisms there are, more of them, then therefore they grow at a greater rate. Now, this is assuming then that as it grows and grows and grows and grows, there is no limit, because if P is 1,000, then it grows at a certain rate. 2,000, it grows at a certain rate. 5,000, it grows at an increasing rate. So, you are assuming that it will grow infinitely. So if you look at this model, right, you're assuming that it grows infinitely. But it is actually a population not in a big pond or something, it's actually in a dish. Correct? Yes? So I think it's reasonable to say that actually there is limited space in the dish. So some of the organisms may die while fighting for food, for space and food. Now, this is not a story, this is not something that we come up with. You may or may not use the exact words. Basically, what you want to say is that this model, all right, you want to answer the question, a condition in which this model may not be appropriate. Essentially, you just want to give the flavor that actually there may be some point, there may be reason why that it cannot depend just on the population. There is a limit to which the population can grow. So therefore, if it will die, some organisms may die without for space and food, the number should reach a maximum after some time. And I think this can be evidently seen in this equation here, if you look at this equation here. Now, sorry, wrong arrow. This one. P is 1000 E ln T. If you sketch P against T, you get the exponential model like that. You are assuming that therefore it can grow infinitely. The population can grow infinitely with no limit, right? Because it's an exponential graph, and it shouldn't be like that if there is a limit to the amount of space and food in the dish. All right? Some time and not likely to increase to infinity. That's that. This is a more comprehensive answer. Your answer may or may not be so comprehensive, but the idea should be there that it should reach a maximum. This one, you just get a flavor will do, like, you just say that there's limited space, limited food. Good enough. You don't need to say it may die and anything. All right, this is just for completeness. That's for question 5.